Hello viewers, welcome to my video. Today we will be exploring about the first theory how our solar system came in its shape. Let's think about this together, and rest of that I will explain next in my video. Have you ever paused to wonder how the solar system, our cosmic neighborhood, was born? Have you ever gazed at the night sky and marveled at the stars, pondering the origins of the planets, moons, and even the Earth beneath your feet? The story of our solar system's creation is as mesmerizing as it is profound. Everything in our world, like mobiles, vehicles, planes, they all have their origins from where they came from, or someone created them. Same like our Earth, it also have its origin, which we all want to know about. For this purpose, many theories are rotating around having a contradiction between all of them. We will be exploring all of them on my channel, one after one, and I will try to resolve this big ever-explained secret about this whole solar system. You will get to know about real facts according to every aspect, science and religion. Now, without wasting time, let's start our video. Imagine the birth of a star, the creation of planets, and the spark of life itself, and everything we see around us. The oceans, the sky, the mountains plus air, water, fire. What if I told you it all began with a swirling cloud of gas and dust? This is the story of the nebular hypothesis, a tale of chaos and creation that shaped our cosmic origins. Prepare for an interstellar journey back in time, where the universe took its first breath. A theory that unravels the magnificent secrets of our cosmic origins. Buckle up for an interstellar journey into the past, where chaos and order dance to create the universe we know today. Our solar system is a magnificent cosmic dance of planets, moons, and countless smaller objects, all orbiting the life-giving sun. From the rocky worlds of Mercury, Venus, Earth, and Mars, to the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, each celestial body is a marvel of nature. Surrounding the planets are intricate rings, captivating moons, and endless mysteries yet to be uncovered. Stretching beyond is the Kuiper Belt and the distant Oort cloud, filled with icy relics from the solar system's birth. It's a breathtaking, ever-evolving masterpiece, showcasing the wonders of the universe. Now let's explore where it came from. It's hard to imagine now, but over 4.6 billion years ago, our solar system didn't exist. The story begins in a quiet corner of the Milky Way galaxy, where a massive cloud of gas and dust, known as a nebula, drifted through space. This cloud begins to collapse under its own gravity. As it contracts, it starts spinning faster, a process dictated by the conservation of angular momentum. This collapsing and spinning cloud eventually flattens into a disk, and at its center, a star ignites. Meanwhile, the surrounding material organizes itself into planets, moons, and asteroids. This process, described by the nebular hypothesis, is the blueprint for the formation of planetary systems. In the 18th century, two brilliant minds, Immanuel Kant and Pierre-Simon Laplace, sought to unravel the mystery of our solar system's origin. Kant proposed that the solar system began as a dispersed cloud of particles. Gravitational attractions caused these particles to collide and bond together, forming larger aggregates that eventually became planets. This hypothesis suggests that stars and their accompanying planets form from massive rotating clouds of gas and dust called nebulae. These nebulae serve as the universe's raw material, undergoing incredible transformations to create solar systems like ours. It's not merely a story about the past, it's an ongoing process happening in galaxies far and wide, proving that our solar system's story is part of a much grander cosmic narrative. Laplace, building on Kant's idea, introduced a more refined model. He envisioned the sun surrounded by an extended atmosphere that cooled and contracted over time. Rings of material, left behind by centrifugal forces, coalesced into planets. His model explained the observed alignment of planets in the same plane and their motion in the same direction. Together, their ideas formed the Kant-Laplace nebular hypothesis, which dominated scientific thought for a century. However, this model faced challenges. It didn't fully explain the retrograde orbits of some moons or the distribution of angular momentum, where the Sun contains most of the mass, yet the planets carry most of the angular momentum. The nebular hypothesis isn't just a tale of physics and chemistry. It's our origin story. Every atom in our bodies was forged in ancient stars, brought together through the collapse of a nebula. It's a story of chaos, creativity, and cosmic wonder that reminds us of our profound connection to the universe. The cloud of nebula like a dust. This was no ordinary cloud. Within it lay the raw ingredients of stars, planets, and even life itself. But how did this cosmic nursery give birth to our solar system? Scientists believe that a nearby supernova, the explosive death of a massive star, sent shock waves through the nebula. These waves triggered a gravitational collapse, drawing the particles inward. And as the nebula contracted, it began to spin, setting the stage for an extraordinary transformation. The spinning motion of the nebula wasn't random. It was a result of the conservation of angular momentum. As the cloud shrank, its rotation sped up, much like a figure skater pulling in their arms during a spin. At its core, pressures and temperatures soared, igniting nuclear fusion. And with that, a star was born. Our Sun. This fiery sphere of hydrogen and helium became the heart of our solar system. Yet, the story was far from over. Surrounding the newborn Sun was a swirling protoplanetary disk, teeming with tiny particles destined to create worlds. Within the disk, dust particles danced and collided, forming larger and larger clumps. Over millions of years, these clumps grew into planetesimals, the building blocks of planets. This was no tranquil process. It was a chaotic battleground of collisions, destruction, and creation. According to the nebular theory, stars form in massive and dense clouds of molecular hydrogen, giant molecular clouds. These clouds are gravitationally unstable, and matter coalesces within them to smaller, denser clumps, which then rotate, collapse, and form stars. Star formation is a complex process, which always produces a gaseous protoplanetary disk around the young star. This may give birth to planets in certain circumstances, which are not well known. Thus, the formation of planetary systems is thought to be a natural result of star formation. A Sun-like star usually takes approximately 1 million years to form, with the protoplanetary disk evolving into a planetary system over the next 10 to 100 million years. Then it comes to the creation of protoplanets. Lucky planetesimals grew into protoplanets, their gravity pulling in surrounding material. Continued growth by accretion led to larger and larger objects. The energy released during accretionary impacts was sufficient to cause vaporization and extensive melting, transforming the original primitive material produced by direct condensation in the nebula. Theoretical studies suggest that several bodies the size of the Moon or Mars must have formed in addition to the planets we know today. These collisions of giant planetesimals, sometimes called planetary embryos, had dramatic effects. For example, a collision of Earth with a Mars-sized planetary embryo could have formed the Moon. Different impacts according to this theory on other planets, where even smaller impacts on Mars in the late phases of accretion may explain the present thinness of the Martian atmosphere. Temperature played a crucial role. Near the Sun, it was too hot for volatile substances like water and methane to remain solid, leading to the formation of rocky terrestrial planets, Mercury, Venus, Earth, and Mars. In the cooler outer regions, gas and ice giants like Jupiter, Saturn, Uranus, and Neptune amass thick atmospheres of hydrogen and helium. The general scheme of planet formation occurred in the outer solar system as well. Here, the accretion of icy planetesimals produced massive objects, with some reaching 10 times the mass of Earth. Their immense gravity caused the surrounding gas and dust to collapse, allowing these planets to grow so large that their composition approached that of the Sun itself, dominated by hydrogen and helium. Each giant planet began with its own subnebula, forming a disk around a central condensation. From these disks emerged the regular satellites, which have nearly circular orbits aligned with their planet's equatorial planes. Irregular satellites, however, were likely captured objects, with some, like Neptune's Triton and Saturn's Phoebe, displaying retrograde motion. Remarkably, the density distribution of Jupiter's Galilean moons mirrors that of the solar system. The inner moons, Io and Europa, are rocky, while the outer moons, Ganymede and Callisto, are half ice. Models suggest Jupiter was so hot during its formation that ice could not condense near Io's current position. Within the disk, dust particles danced and collided, forming larger and larger clumps. Over millions of years, these clumps grew into planetesimals, the building blocks of planets. This was no tranquil process. It was a chaotic battleground of collisions, destruction, and creation. The lucky planetesimals grew into protoplanets, their gravity pulling in surrounding material. Continued growth by accretion led to larger and larger objects. The energy released during accretionary impacts was sufficient to cause vaporization and extensive melting, transforming the original primitive material produced by direct condensation in the nebula. Theoretical studies suggest that several bodies the size of the Moon or Mars must have formed in addition to the planets we know today. These collisions of giant planetesimals, sometimes called planetary embryos, had dramatic effects. For example, a collision of Earth with a Mars-sized planetary embryo could have formed the Moon. Smaller impacts on Mars in the late phases of accretion may explain the present thinness of the Martian atmosphere. As the nebula condensed under gravity, it spun faster due to angular momentum, forming a flattened, rotating disk. At the center, temperatures and pressures soared until nuclear fusion ignited, birthing the Sun, a blazing sphere of hydrogen and helium. This central star illuminated the protoplanetary disk surrounding it, setting the stage for the creation of planets and shaping our solar system as we know it today. Temperature played a crucial role. Near the Sun, it was too hot for volatile substances like water and methane to remain solid, leading to the formation of rocky terrestrial planets, Mercury, Venus, Earth, and Mars. In the cooler outer regions, gas and ice giants like Jupiter, Saturn, Uranus, and Neptune amassed thick atmospheres of hydrogen and helium. The general scheme of planet formation occurred in the outer solar system as well. Here, the accretion of icy planetesimals produced massive objects, with some reaching 10 times the mass of Earth. Their immense gravity caused the surrounding gas and dust to collapse, allowing these planets to grow so large that their composition approached that of the Sun itself, dominated by hydrogen and helium. The formation of planetary rings remains a subject of intense research. Their existence is closely tied to their position relative to the planet they surround, specifically within a region known as the Roche limit. This critical distance, first explained by 19th-century mathematician Edouard Roche, is where the gravitational forces of a planet prevent small bodies from coalescing. Within this zone, the gravitational attraction of the planet disrupts accretion, ensuring that small particles remain dispersed. For Jupiter, Its rings are in a steady state of particle production and loss, replenished by the planet's inner moons. Saturn's rings, however, may be relatively young, possibly only a few 100 million years old, formed from icy planetesimals that collided and fragmented. Understanding how these particles are radially confined and how ring systems evolved continues to challenge astronomers, highlighting the dynamic processes shaping our solar system. What makes this theory so compelling is its universality. It doesn't just apply to our solar system, it applies to countless systems scattered across the universe. Every time we observe a young star surrounded by a protoplanetary disk, we're witnessing the nebular hypothesis in action. It's a cosmic story that echoes across the vastness of space. Recent observations have provided astonishing evidence supporting this hypothesis. Advanced telescopes, such as the Atacama Large Millimeter Array, have captured images of young stars surrounded by disks of gas and dust. These disks reveal gaps and rings, potential markers of planets forming within them. Each discovery deepens our understanding of how worlds come into existence. The nebular hypothesis isn't just a tale of physics and chemistry, it's our origin story. Every atom in our bodies was forged in ancient stars, brought together through the collapse of a nebula. It's a story of chaos, creativity, and cosmic wonder that reminds us of our profound connection to the universe. The nebular hypothesis doesn't just stop at the birth of planets and the sun, it hints at the emergence of life. As the young Earth cooled and stabilized, it retained a thin atmosphere and water-rich conditions, crucial for the origins of living creatures. This grand cosmic choreography set the stage for life's remarkable diversity. The dust, gas, and materials left over from the solar nebula gave rise to organic compounds, the building blocks of life. Over millions of years, chemical reactions in Earth's oceans sparked the first primitive life forms. From microorganisms to complex multicellular organisms, the evolutionary journey began. It's astonishing to think that everything, from the smallest bacterium to the vast biodiversity we see today, owes its existence to the processes described by the nebular hypothesis, linking all living beings to the stars. Before this story ends, did you know? Laplace's nebular hypothesis was so influential that it remained largely unchallenged for over a century, despite being purely theoretical at the time. These early ideas, though incomplete, set the stage for modern astronomy. Over time, advancements in technology and science allowed us to refine the hypothesis, leading to the development of the solar nebular disk model we use today. This updated framework incorporates data from space exploration, telescopic observations, and computational simulations, bridging centuries of inquiry into a cohesive theory. The nebular hypothesis was largely abandoned by astronomers at the beginning of the 20th century due to its inability to explain the distribution of angular momentum between the Sun and planets, and unfortunately, this theory was rejected by Chamberlain Moulton. In 1900, Forrest Moulton showed that the nebular hypothesis was inconsistent with observations because of the angular momentum. By the way, this story of the universe connects us all, reminding us of our shared cosmic heritage. From the birth of stars to the creation of planets, the nebular hypothesis unveils the magic of how it all began. So, the next time you look up at the stars, remember, you're a part of this grand cosmic tale. This was the first theory that was made by humans related to the birth of our Earth and our solar system. I will be explaining other theories in my next videos. Thank you for joining us on this incredible journey through the origins of our solar system. If you enjoyed this video, don't forget to like, subscribe, and follow us for more updates on the fascinating theories and mysteries of our incredible world. Your support helps us explore the universe together. More videos will be coming soon. Until next time, keep looking up.